qualcosa o...
No. Ah. Okay.
Morning, everyone. Please take a seat if you have not done so. Thank you. Welcome, everyone, to the Astronomy for Non-Astronomers. So today I will be presenting to you Paolo Padovani. If you are an astrophysicist, you probably have heard his name already, especially if you're an early career scientist, because that means you probably have seen his name on course books about AGNs. And that's basically, I think, all his science is AGN from gamma to radio, and even touched neutrinos, as I understand, especially collaborating with TUM. So on the 1st of December, Paolo Padovani will be 20 years in ESO. Is now working as in the ELT science office. And outside of science, is very interested in dissemination, both in schools and in public talks. So that takes me to introduce the talk of today, where he will take us on a journey, on a very, very long journey, from the beginning of the universe until today. And so please give him a warm welcome, and thank you, Paolo.
Good morning, everybody. Welcome. So today I'm going to tell you a story. We humans like stories, but it's not any story. It's the mother of all stories. If what I'm going to tell you today hadn't happened, there would be today nobody here to listen to the story or to tell the story. It's a story of how we got from the beginning of the universe to us in about less than 14 billion years, compressed in 45 minutes. It's a very complex story, which I made, of course, understandable to you all, but it will require you to be very focused and attentive for about 45 minutes. So put away your cell phones now. And I'll highlight the major events, which, in my opinion, are the ones without which we won't be here today. That's the main message of the talk. Before I start, though, something about language. As all astronomers know, and all scientists, everything in the universe is about physics. The sun is a gigantic nuclear reactor. Driving a car is about physics. Playing tennis, you have to deal with the gravity of Earth, which is going to try to pull the ball to the ground, friction of the air, light from the sun, the torque of your elbow. Everything is physics. And the language of physics is math. The universe is talking to us using mathematics. And this was understood, actually, a long time ago by Galileo Galilei. L'universo scritto in lingua matematica. So what I had to do today was to translate from math to an everyday language to make, of course, these complex concepts, which we understand by writing down equations, to you all, because this is not your topic. And I try my best to do that. And I also want to be using analogies, but I still want to give you some numbers. So you see many numbers about time, distances, masses, energy, so you have an idea of the scales of the things we're talking about. Okay, so top right, you see the age of the universe. That's the beginning, t equals 0. You see anything? No, because there is nothing to see. There is no here, there is no there, there is no radiation, there is no matter, there is absolutely nothing. Something which we can't imagine because we're not used to nothingness, right? There is nothing. Every now and then, out of this nothing, a perturbation, a fluctuation appears and then disappears. It's allowed by the laws of physics. But then, for some reason, one of these perturbations stays. It stays there. That perturbation as the seed of everything we know, everything that has ever been on Earth, everything that will ever be on Earth, everything is there. The seed of everything that we actually know and we ever know is there. But to be honest, we cannot go down to t equals 0. We can only go down to 0.4201 seconds. Below this value, which is called the Planck time, there is nothing we can know and understand. Long story, because basically below this time, we cannot merge gravity with quantum mechanics, and so we cannot understand how things are working. So we start from this, which is not too far from 0, to be honest. I mean, it could be worse. So this is the earliest where actually we can study the universe. 10 to the minus 43 seconds. That's how we write it in the scientific notation. This thing is hot, but hot is an understatement. I wrote there billions to billions to billions. It's super, super hot, more than we can imagine. And it's tiny. It's smaller than the dimensions of an atom by billions of orders of magnitude. So when we give these talks, it sounds like we know everything, which is not true. There are many things we don't understand. So every now and then you see this banner coming out, and I'm going to highlight the things we still do not understand. How this fluctuation came, where it came from, why it stayed, we don't have a clue. We don't have a clue, so it's an open problem. And you see during the talk, every now and then, this banner coming out, so you actually you appreciate the fact that there are still many things to study and many things we don't understand. Okay, so this thing, whatever it is expanding. It's not standing still, it's becoming bigger with time. And I'm going to explain to you what's happening in the first moment of the universe by I have to use two laws of physics. One is the equivalence between mass and energy, E equal mc squared, where c is the speed of light. This is the most famous and least understood equation of history, I think, because very few people understand what it means. It means simply that you can go from mass to energy, from particles to radiation. You can exchange the two. The way you do it is complicated, but that's the message. Second one is conservation of charge. The universe is neutral. If I create a positive charge, like a proton, I need to create a negative charge to conserve the number of charges, which has to be 0. So based on these two laws, I'm going to tell you the first moments of the universe, which is a complete mess, right? Because you have many things happening. You have radiation, because this thing is hot, and photons have the habit of colliding between two photons and producing pairs. So two photons will collide and produce a particle and an antiparticle, matter and antimatter. Energy, charge is conserved because you have a proton and an antiproton, and you're using energy goes into mass, radiation goes into particles, E equal mc squared. Fine, so we understand this very nicely. But the two particles just created, matter and antimatter, don't like each other. When they meet, they annihilate, and they produce radiation. Now you have mass going to energy, particles going to radiation. Now imagine this is called the primordial soup. You have the interactions happening constantly. Radiation becomes particles, particles becoming radiation all the time. It's a total mess. But there is one thing. The universe is expanding, and the higher the temperature, the higher is the energy of the radiation, the higher is the mass of the particles you can create. But something which is expanding will lower its temperature. If I have a ball of gas, a balloon, and I double its volume, the temperature is going to go down. So this thing, which was really, really hot, really, really small, is becoming bigger and cooler. But cooler, of course, is a relative statement. By the time the universe is 0.0001 second old, the temperature is only 4,000 billion degrees. That's more than we can ever have in the universe these days. Why is this important? Because below this energy, radiation cannot produce protons and antiprotons any longer. The energy of the radiation is not enough to create these particles. So now, the photons produce this matter and antimatter. That's it. They cannot produce them anymore. So you have the universe filled with protons and antiprotons, right? And they do what they're supposed to do. They annihilate and produce radiation. If this were true, we would be here today. Because every proton will annihilate with the antiproton and there will be no matter left. Now, every time I tell this thing, I get the shivers. Out of 1 billion pairs of protons and antiprotons, there is a single unpaired proton. It's there. It doesn't have a counterpart to annihilate with, and it stays there forever. According to the laws of physics that we know, we shouldn't be here today because this matter-antimatter asymmetry is not understood. It's an open problem. Nobody knows why, out of these billion pairs, there was this single proton which was unpaired and then remained there forever. Really, nobody knows how. There are many ideas around, but nobody knows why. But I state again, according to the laws of physics we know, we shouldn't be here today because there should be no matter in the universe, just radiation. And this is not the case. Time goes on. Wow, the universe is 100 seconds old. It's getting, oldish enough. And now another mark in time, a landmark, temperature is 2 billion degrees, which is actually now getting closer to what we found in some stars as well. And the creation of electrons and anti-electron stops. Why? Because the electron is a factor of 2,000 smaller in mass than the proton, so the temperature can be lower. So, now you understand that, every billion pair of electron and anti-electrons, you have a single unpaired electron, and it stays there forever. So, after all this mess, we're left with protons, neutrons. Yes, there is an anti-neutron, even though the neutron is neutral. Long story. It's made of antiquarks, but that's the detail. So we are left, after all this mess, 100 seconds, protons, neutrons, electrons, radiation, light, and neutrinos. Neutrinos we don't care. I do care for other types of neutrinos, but this is what we're left off with after 100 seconds. So at least some particles and something which we can understand. It took 100 seconds to get to a universe which we can start to imagine at least. Now, of course, the universe keeps expanding, temperature keeps going down. So now I have to explain you other processes which are going to happen. And I need to remind you what an atom is. An atom is the fundamental thing which is the base of elements. It is made up of a nucleus, which includes protons and neutrons. Protons are positive charged, neutrons are neutral. And around this atom, there is a cloud of electrons, which are negatively charged. And the number of electrons is the same as the number of protons, because atoms are neutrally charged. The total charge is 0. 2 pluses, 2 minuses, total is 0. And I guess most of you have seen this at least once in their lifetime. This is the periodic table of the elements. And there we have all the elements we know, and they're sorted by the number of protons. So hydrogen has 1 proton, 1. Helium has 2. Carbon has 6. Nitrogen has 7. Oxygen 8, and so forth. The most important thing to remember is that now the chemical properties of elements are dictated by one thing, the number of protons in the nucleus. So the alchemists in the Middle Ages, where they're trying to convert lead into gold, easy, right? Lead is plumbium here, there. Proton number 82. you remove the three protons, and you get aurum, gold. And you can do it, of course. You can do it these days, but the process is not very efficient. You waste more energy doing the conversion than using the gold that you're going to be able to sell. So long story, but anyway, you got the idea. If you remove or you add protons to an element, the element is going to change completely its chemical properties. And this will come back later. So time goes on. Now the time is between 3 and 20 minutes. And the first atomic nuclei, apart from hydrogen, are being made up. Why? Because a proton is the nucleus of hydrogen, okay? It's one proton. Hydrogen has atomic number of 1, so it's the nucleus of hydrogen. But now the universe is trying to make other elements. And then the next one in line is helium. Helium has 2 protons. So what happens? The universe is still hot enough. He has to convince a proton and a neutron to form deuterium. The deuterium now, as you can see, has a proton and a neutron. A proton is positively charged. So 2 nuclei of deuterium will try to repel each other. But the universe is hot enough, it's going to convince the 2 to fuse together, and at the end of the day, you have helium, 2 protons. Helium-3 because 2 protons and a neutron, but it doesn't matter. What's important is that before we only had nuclei of hydrogen, now we have nuclei of helium with 2 protons. And so now you might think, okay, now the universe is going to make all the elements we know. Unfortunately, not, because the temperature is going down. And if the temperature is going down too much, the universe won't be able to convince positively charged particles to fuse. And that's it. The universe can make some helium and then something else. I'll get to that in a minute, but then that's it. In the meantime, time goes on again, 300,000 years, and the first elements, remember, so a nucleus is proton, neutrons, elements are a nucleus with the electrons around. Until now, there were no elements, because when the electrons were trying to get together to form an element, they were destroyed and removed by the radiation, which was really, really hot. Now the universe has cooled down enough, only 3,000 degrees, which is okay, and the first elements now can form. But since the nuclei to build the elements were what they are, at this time, the universe is made up of 3/4 hydrogen, 1/4 helium, a sprinkle of lithium, and that's it. So we have a problem, right? Because we are made mostly of oxygen, carbon, nitrogen, phosphorus, whatever. So where are these elements coming from? And the elements are coming, well, will be made thanks to gravity. I haven't mentioned gravity yet. Why? Because at these times, gravity is completely irrelevant. Before you have elements, and when you have free particles, let's calculate, so protons are going to be repelling each other because they have a plus charge. Gravity will try to get them together because gravity attracts things. If you take the ratio between the repulsion and the attraction, you get this value. 1 followed by 36 zeros. Gravity is the weakest force in the universe, and before there are elements, it's completely useless. It doesn't do anything. But once we have neutral things around, the charges disappear, and gravity slowly starts to work. And gravity is going to be the queen of the next moments in the evolution of the universe, and the one responsible for the other elements in different ways, which I'll try to explain to you. Okay, now 380,000 years after the Big Bang. This is a map which gives us the temperature of the universe, actually the difference in the temperature of the universe in different locations. So red spots are slightly warmer, green spots are slightly cooler. The difference is 0.0005 degrees. So the universe is almost at the same temperatures, but not quite. There are some parts which are slightly warmer and some parts which are slightly cooler. And this means that the universe is not homogeneous density-wise, because things with different temperatures at different densities. And so the universe is not like a beach where you have grains of sand with the same density everywhere. No, there are some parts which are slightly denser, more matter, and other parts where there is slightly less matter. And the way I like to explain this to you is, imagine you have a very thin rubber sheet, very, very big. And then you throw pebbles on this rubber sheet. The bigger pebbles will make bigger holes, right? Bigger dents, bigger depressions. And if there are smaller pebbles nearby, they're going to be attracted and fall with the bigger pebbles. And so the more time goes on, the bigger depressions will become even bigger, because the bigger you are, the more you attract stuff, and then you get bigger and you attract more stuff. So it looks like this thing is going to end up with a huge depression where all the matter is there. No, because the universe is expanding, and so the rubber sheet is going away. So you have gravity trying to attract things, and the universe pulling them away. And this means, in a very complicated way, that the first condensations of matter actually arise, and after a certain point they stabilize, because they cannot attract anything anymore, because the universe has pulled away the matter. So after the first 380,000 years and more, a universe which was almost homogeneous now has clumps of stuff, where there is more matter than in other locations. And this leads us to the first stars. So we believe that around 200, look at the time now, we went from 380 to 200 million years, so way, way, way forward. Our theories believe that around that time, the first stars were born. How? It's a very complex thing. So what you want to do, you want to take matter and compress it so that the core has a temperature about 5 million degrees. That's where any object will become a star, for reasons which I'll describe in a second. This thing has a very complex process. Once you compress the stuff, matter around this area will become hotter, and so we'll try to move fast and escape the compression. So first you need to cool the stuff so that the core can become very hot. It's a very complicated thing, and now you guess it, open problem. We still don't know how we can make the first stars. We haven't seen them yet. We have many ideas, but we still don't know. Now, I'll have to tell you what stars are. And I'll give you a definition which I think you're not used to. Stars are objects in perfect equilibrium. There are two forces working on a star. Gravity is going to want to pull all the matter in the star to the center. And pressure, due to the gas and the radiation inside the star, is going to push stuff away. The radius of a star is the distance from the center where the two forces cancel out. So a star is an object which is in a perfect equilibrium under two forces, gravity, which wants to compress, and pressure, which wants to expand. And this will come back later. Of course, stars are also very important because they create energy, right? So in the sun, for example, you have 4 protons becoming an atom of helium and producing energy. Again, 4 protons are positively charged. They don't want to stay together. So the fact that the sun is so hot, 5 million degrees, means that it's going to force these protons to get together. And once they're close enough, the strong force is going to take over and it's going to glue them together. And then you go from 4 atoms of hydrogen, 4 protons, to an atom of helium. Every second, the sun converts 600 million tons of hydrogen into 596 million tons of helium. There are 4 million tons missing here. Where are they gone? They go into energy. The trick is that 4 protons weigh slightly more than an atom of helium. The difference, E equal mc squared, is the energy that actually we all use, right? So a tiny amount of mass multiplied by a big number gives you the energy that the sun is going to give us, has given to us, and will give us for a long, very long time. So the sun is a gigantic nuclear reactor. Around the same time, the first galaxies also are being put together. A galaxy is an ensemble of stars with the planets around it and the comets and the asteroids, everything together. So you're all familiar with it. This is a picture of some galaxies. And we have also a picture of the most distant galaxy ever observed, which is this one. That little blob there. It's a galaxy which actually was, which detected at the time when the universe was 320 million years old. The last time I gave this talk, the number was 400 million. This is an observation by JWST, the James Webb Telescope, is pushing the limit even closer to the Big Bang. So we know for sure that 320 million years after the Big Bang, there was a galaxy and it is this little red blob there. But I just said that we know we went back in time to a time when the universe was 320 million years old. So how is it possible? Well, because it's obvious we have, as astronomers, we have a gigantic time machine at our disposal, the universe. You've seen movies where people go back in time, blah, blah, blah. We actually are lucky, and we actually can go back in time for a very simple reason, that everything in the universe, the information goes at the speed of light. The speed of light is very fast, but not infinite. It's about 300,000 kilometers per second. That's a lot. You're on the moon. You go around the Earth 7.5 times. This delay, this speed, which is limited, the light from your colleagues up there, they're not going to reach me instantaneously. It gets to me like after a few microseconds. There is a delay, right? Okay, you say, okay, but everyday life, we don't care. Yes, okay, but if the sun disappears now, we will know about it in 8.3 minutes. And if you want to send a message to Saturn, light is going to take about 67 minutes to get to there, at the closest. So this is actually very relevant. If you have a space probe, which is going around Saturn, and you need to turn on the engine at a given time, you can't press the button at the right time. You need to press it at least 6-7 minutes before. That's the time that the message is going to take to get to Saturn and then turn the engine on. That's obvious. So we deal with these things routinely when you talk about space missions. The closest star, Proxima Centauri, we see it as it was 4 years and 3 months ago, and the closest big galaxy, Andromeda, as it was 2.5 million years ago. Which means, and when I talk to kids, they love this, if there was an astronomer now on Andromeda at this second, looking at us with a big telescope, he would see this. He would see our ancestors, right? Because the light that they got to Andromeda took 2.5 million years to get there. It would see Earth as it was 2.5 million years ago. And again, so we have a time machine at our disposal. The further you go in distance, the more you go back in time. So now, let's get back to the core of the talk, right? So 400 million years have gone by, we have stars, we have galaxies, but we still have this problem. We have the universe made up of 3/4 hydrogen, 1/4 helium, and a sprinkle of lithium. How do we get to the next step? And just to remind you, I love this picture. It shows the percentage of elements in our bodies, on average. So we're made up of water, as you can see, 62%. But then if you look at the elements, oxygen, 65%, carbon, hydrogen, nitrogen, calcium, phosphorus, these 6 by themselves is 98.4%. So, but we need more. The other ones on the right, we also need potassium and others in small doses, but we still. So where are these coming from? Where is the oxygen that we breathe? Where is it coming from? And so, to tell you, I need to give you a crash course on stellar evolution. So, in the universe, nothing is eternal. Everything is born, it grows, up, it evolves, and then it dies. And stars are not an exception. So stars are born, for example, in the Orion Nebula, which actually you can see with the naked eye in the winter at our latitudes. And then they evolve. Why? As I said, the sun uses up 600 million tons of hydrogen a second. The sun is big, okay? The mass of the sun is 2 followed by 30 zeros kilograms. It's enormous. But time is not infinite. I mean, it's using up material, and after a while, it runs out of fuel. So when a car runs out of fuel, it stops. And the sun, when it runs out of fuel, it contracts. Why? Because remember that stars are things which are in equilibrium. Gravity wants to pull them together, and the pressure of the hot stuff inside wants to push them away. If you switch off the engine, no more pressure, the star will start to collapse and contract. So it gets smaller. It gets smaller, but when something gets smaller, it gets hotter. So the temperature increases. And then magically, new reactions start. Until now, the sun was burning hydrogen into helium. Now it doesn't have any more hydrogen, it's just helium. So the next reaction is going to start, and I'll tell you in a minute. And the star can resurrect because now it's emitting radiation, the pressure is increasing and increases so much that it goes beyond the radius we said before and becomes a giant. So let's get again to the core, to the other elements. So at this stage, what the sun will do is the following. As I said, the sun is now full of helium, atom of helium. So 2 atoms of helium, thanks to the temperature, which has increased now to a level which I'll tell you in a minute, will become an atom of beryllium. Beryllium will smash with an atom of helium and will create carbon. Carbon-12, 6 protons and 6 neutrons. Remember that the elements, the properties depend on the number of protons. Now you require 100 million degrees. Before, 5 million were enough because you had 4 charges to convince to fuse. Now you have 6, and you need much higher temperature to convince this reaction to happen. And then things goes on, okay? Like every cycle is going to last less and less because the temperature is higher, the consumption is larger, and then you have other cycles where you actually burn carbon with helium, you create oxygen, oxygen with helium, you create neon, and so forth, all the way to iron. Every time, the temperature has to increase because every time the number of protons you want to convince to merge increases. For example, a big star, after various billions of years, is going to make up, like we say, we're going to have an ion structure. So an anion structure. So the big elements at the center and the lighter one at the edges. So you go from iron, silicon, oxygen, all the way to hydrogen at the edge. And just for your information, the oxygen we breathe now, was created inside the star at about 1 billion degrees. So every single atom we breathe comes from a star and it was created at this temperature. Okay, but this is not enough. Stars are making elements, but then if they kept their elements inside the stars, then we won't be able to reuse them, right? So what's happening is that
about 2 or 3 times a century, a massive star in our galaxy explodes. The star's core may survive as a neutron star or a black hole, but the rest of it rushes into space as swiftly expanding debris behind a powerful shockwave. As the supernova remnant grows, it sweeps up interstellar gas and gradually decelerates. Yet,
okay, so big stars with a mass above 8 times the mass of the sun, die this way. Again, it's a very complex phenomenon. Once you get to iron, to the fusion where we produce ion, things get complicated. Before the reaction, we're producing energy. Now they are requiring energy. In a few seconds, the whole star collapses and then bounces back, and most of the mass of the star is thrown out in space to be able to be reused by other stars and to end up, at the end of the day, in our bodies. And we see that. This is a beautiful image in the X-ray band done with the Chandra telescope. The different colors correspond to different elements. So here we see silicon, sulfur, calcium, and iron in the supernova remnant, in the material around the stuff which has been thrown out after a supernova explosion. So actually we see that, and these elements go back into space to be able to be recycled. Now, what's left after this explosion? It's quite interesting and relevant for our story. If the mass of what's left in the nucleus is smaller than twice the mass of the sun, and I remind you, the mass of the sun is 2 followed by 30 zeros kilogram, then you have a neutron star. If it's above, you have a black hole. Black holes, I won't talk about black holes today because they're not relevant to our stories. I love black holes, but they're not what we want to discuss today. Neutron stars are relevant to us. What is a neutron star? So remember the atoms. You have protons and neutrons in the nucleus and electrons around them in a sort of cloud. When this compression happens and you have this core, the density gets so high that the electrons and the protons are squashed together and they produce a neutron and then a neutrino. The neutrino goes away and you're only left with neutrons. And so while in stars, the pressure of the hot stuff and the radiation was fighting gravity, now it's the pressure of the neutrons all stuck together, which stops gravity from creating a black hole. So this is what the neutron star is all about, and it's 20 kilometers. The sun has a radius of about 700,000, and so the density is amazing. 1 cubic centimeter, okay, it's about 10 billion kilograms. When I go to schools, I say, guys, a cube with 3 centimeters on the side weighs more than all the humans on Earth, okay? A cube with 3 centimeters per side. So it's a very, very dense stuff. But why do we care about neutron stars? Well, we do care because, again, for the elements. So again, this is the table, but now this is color-coded, done by a colleague, an astronomer colleague. And now it's color-coded according to the origin of the elements. And as you can see, supernovae can only get up to rubidium, and they cannot make all the elements which are heavier than that. For example, gold, lead. One thing which actually I was interested in, iodine. Without iodine, we cannot grow. It's fundamental for our growth. So iodine is not made by supernovae. It's made in neutron stars in a way which I'll tell you in a minute. Another one was moblidium. I found it at the end the other week in a food supplement. You have vitamins and moblidium. You need moblidium to do, I don't know, whatever. I never heard about it, but it's again made in, not in stars, but in another way. What is this way? I hear say problem almost solved, because until now it was not clear which process was making these heavy elements. And now most astronomers at least agree that it was made by neutron stars in this process. Nando discussed this last month. You have two neutron stars, they get together, they spiral in. And they produce new elements. Again, the mechanism is very, very complex. A neutron star, I said, is made of neutrons, but at the edge, there are still other elements left over from the star. So what's happening, and this movie shows you, but I can tell you in words, there are processes which basically transform lighter elements into heavier elements, and you get from a position where you only had elements down to rubidium, all the way up to much heavier elements. All this is done in about 40 seconds at a temperature of about 1 billion degrees. The main message is that only neutron stars mergers can produce the heavy elements, which some of them actually end up in our body as well and are very useful to our survival. Okay, so time goes on. Now we go to 9.3 billion years. And something happened in the universe which is not relevant for the universe, it's relevant for us. A special star is born into a biggish spiral galaxy, about 2/3 from the center, and this star, of course, is the sun. The sun is a latecomer in the universe. The universe was quite old at the time, and the way the whole thing is formed in the solar system and so forth is very, very complex. This beautiful slide from NASA tries to explain it, and it's very, very complex. You get it, it's an open problem. The idea, again, in a nutshell, you have a cloud, a molecular cloud sitting there, doing nothing. Nearby, a star goes supernova, squashes the molecular clouds, which starts compressing and rotating, and at the center, you have more accumulation of matter. You create what's going to become the sun, and in this disk, which forms, you have other things, smaller things, planets, and to make a very long story short, you get the solar system. Again, as I said, it's a very complicated thing, and it's not, we still don't understand all the details, which are very, very complicated. But after a while, and after a beginning which is very, very chaotic, you have our solar system with the sun and the 8 planets, sorry, not 9. And I was in Prague when we demoted Pluto to a minor planet, and they convinced me, the expert, that this was the case to do. So we only have 8 planets in the solar system now, and Earth is there. But let's think about something. So Andromeda Galaxy again. The Andromeda Galaxy is about 1,000 billion sources. Our galaxy is slightly smaller. Stars, sorry. Our galaxy has about 200 to 400 billion stars. And we know that there are about 2 trillion galaxies in the universe. So the number of possible solar systems is huge, right? But believe it or not, until 1995, we knew only one, and some people were saying it was the only one in the universe. I can't believe that a posteriori, but some scientists were saying we are the only ones, there is no other solar system. Then everything changed thanks to discovery made by people who got the Nobel Prize, and now we know a bunch of planets rotating around other stars, and this beautiful movie is there. Sorry. And as I said, and of course, big question that I always get asked about life, right? So astronomers came up with the idea of the habitable zone, which is the zone around the star where you can have liquid water. You say, why? Because the only life we know is ours, and without liquid water, you can't have any life. So this shows you that for the sun, the habitable zone is including the Earth, of course. It's touching Venus, and it's including Mars. So already understanding that habitable doesn't mean inhabited. There is something else going on, right? But the good thing is that by looking at these exoplanets, we found that about at least 1 out of 10 of the stars has an Earth-like planet, a planet which is similar in size to the Earth, within the habitable zone of the star. So in theory, every star out of 10 could have another Earth. But as I said, things are a bit more complicated. Let's look at Mars. Mars is in the habitable zone of the sun. Temperature is about minus 80 degrees on average, and it sometimes gets about above zero at the equator. We know for sure, these are pictures of Mars probes, that there were rivers there. These are dried up rivers. They look exactly the same as the dried up rivers on Earth. So until a few billion years ago, there was water flowing on Mars. It's gone. Why? Well, the main idea is that the sun is throwing out particles all the time. It's called solar wind. Our Earth has a magnetic field, which protects us from the solar wind. Mars had the magnetic field. He lost it. And so the solar wind removed the atmosphere and all the water evaporated. So again, how you go from being habitable to being inhabited is a very, very complex topic. Again, another open problem. So, guys, you made it. So we went from Big Bang to now in less than 45 minutes, yes. And I think every time I give this talk, I think humanity should be extremely proud, because a bunch of atoms of carbons, nitrogen, oxygen, phosphorus, after a time travel of 13.8 billion years, can manage to look back and ask themselves and give the answer, where are we coming from? We know where we're coming from. So we've gone through a lot of topics. As I told you at the beginning, you would have left. We covered quantum mechanics, primordial nucleosynthesis, structure formation, extrasolar planets, stellar evolution, supernovae, and also I hope I convinced that there are many things we don't understand. So, like, humanity should be very proud of yourself, because you managed to follow me over these very complex topics in 45 minutes, and you're still there. Thank you very much.
Thank you. So I think we have some time for questions.
I'm not taking questions from astronomers, I tell you already. So only non-astronomers are allowed to ask questions. Okay, go ahead.
So